Hi everyone, today we're talking about correlation and we're kind of building off of yesterday's activity. We're talking about our Barbie bungee jump and we're saying how can we be sure that the bungee cord that we make our Barbie is going to keep her safe? Should you be worried if you use the wrong units, choose the wrong axes, or measured wrong? What do we think about this? So let's take one group's data from yesterday measuring their Barbie's distance and hang time using those 7 rubber bands that we used, okay? And let's go to Staplet and create a scatter plot and sketch it to the right. So in Staplet, you're gonna choose that 2 quantitative variables and input for the explanatory, the number of rubber bands, and the response is the distance traveled. And then you should get something like this right here. And we're gonna just take a second. It says find the correlation R, and if you look below, Staplet tells you that your R value is 0.992, and I know that you guys know a little bit about this from previous lessons, and now we're just going to go into it a little bit further. How safe do you feel Barbie's bungee jump would be if we use this data, use that correlation to justify? So we would probably feel pretty safe because we've got a strong R value, 0.992, shows us that there's a strong correlation between the number of rubber bands and that distance traveled. Okay, so we're saying like, oh, okay, there's a strong correlation between the number of rubber bands and distance traveled. So maybe I feel comfortable using this linear model here to predict for an even further distance or even more rubber bands, right? So I can talk about that. One of the group members snuck some extra rubber bands to collect more data. Add the point 1549 to your scatter plot. How do you think this outlier is going to affect the correlation? So 1549, when you add that outlier in, it's like somewhere like way out here. Further away, both in the X and the Y direction. But you notice that the value falls in line with your other values. So we would expect this outlier to make the correlation even stronger. Because it's just proving that linear relationship is occurring even further out. And that's since that value falls in line with that linear pattern. Strengthening that pattern even further, okay? And you should see that your R is 0.998. So it did indeed get a little bit higher than it was before. It was 0.992, and adding that 0.998 made that correlation even stronger. That's one key, is that outliers, although this might be very far away, if they fall in line with the linear pattern, they increase that correlation. Okay, it strengthens that correlation. One group member accidentally left off a digit, and we're going to add the point now, 6,6. So 6,6 is right here. What would we expect to happen to the correlation? And what we should expect is that we would expect that this would make the correlation even weaker. And why is that? That's because correlation is a measure between two variables and the extent to which they have a linear relationship. So if a point falls outside of that linear pattern, that brings down the correlation. Okay? And we can verify that. When I look at my original data and then just add that 0.66 in, my correlation drops to 0.499. So that's pretty big of a drop. When I calculated that correlation coefficient, I didn't include this point. I just looked at the original data and saw how it would move, okay? So let's keep going. It says, unfortunately, the group had measured the lowest point of Barbie's head in inches instead of centimeters, not following directions. So to fix this, they multiplied inches by 2.54 because 1 inch equals 2.54 centimeters. And here's our new data below. How do you think these changes will affect the correlation? Verify by calculating the correlation in the applet. Okay, so what you're going to do is you're going to go ahead and enter these values into Staplet, and let's see what the correlation is. And I end up seeing that R equals 0.992, and I'm like, oh, it didn't change, right? So the correlation didn't change because that actually makes sense. Units don't really matter when it comes to correlation because the relationship that the points have to each other does not change. Even if I just change the units, the points didn't move further or closer away from each other, okay? So on this page, we've learned quite a few things, okay, through just observation. And the first one is that our correlation coefficient is affected by outliers. If the outlier falls within the pattern, then it's going to strengthen the correlation. If our outlier falls outside of the pattern, it's going to drop the correlation. And the correlation coefficient is not affected by units, okay? Units doesn't change the relationship the points have to each other. All right, let's go to the next page. Let's get some formal notes down on how to interpret that R correlation coefficient that we were calculating right there and what it means for us. Okay, that R stands for the correlation coefficient. And what that does is that tells us the extent to which there is a linear relationship, okay? So R is the variable representing the correlation coefficient. All right, and here's some properties that are true of that correlation coefficient, okay? The correlation coefficient does not have units. So just like we saw in the last example, if you change the units, R stays the same because it's measuring the degree of a linear relationship, okay? So the points are still having that same linear relationship if we switch the units up. It's like a shift almost. Another thing is if you accidentally switch those X and Y axes, you'll still get the same R value. So let's say you confused the explanatory with the response variable. Other things will be affected, but the R value will stay the same, okay? Switching axes does not change the R value. Okay. R is non-resistant to outliers. So if you throw an outlier in there, stuff is going to happen, okay? If the outliers are in the pattern, that strengthens the correlation. If the outlier is outside of the pattern, that weakens the correlation. Okay, because remember, R is the degree to which we have a linear relationship, the measure. The closer R is to 1, the stronger the linear relationship. So let's talk about how we can interpret R, okay? So R, first of all, it tells us the direction of the correlation, okay? So if R is positive, then the correlation and the linear relationship is increasing. That line that we're kind of seeing being created by that data is representing increasing data. And so if we were to make an equation, the equation would have a positive slope. If R is decreasing, if the linear relationship is decreasing, R should be negative, and we would expect a negative slope. Okay, R also tells us about the form, which is linear, right? So R measures the degree of which there is a linear relationship. Okay, between two variables. Two quantitative variables. So that means that R doesn't necessarily measure the degree to which two variables are related if it's not linear, okay? It only measures the linear relationship. And R also tells us about the strength of that linear relationship. We have this kind of standard scale that we follow right here. 0 means there's no correlation at all. Okay. Between 0 and 0.5, either in the positive or negative direction, indicates kind of a weak linear relationship. And this direction would be a weak negative or a weak positive relationship. Between positive and negative 0.8 and 0.5, we see a moderate relationship. So here we've got moderate negative, moderate positive, and then above positive or negative 0.8 is not 0.1, it's 1.0. We have a strong linear relationship, positive or negative. And if you have a linear relationship of 1, either positive or negative, that's perfect. Every single point lies perfectly in a line, perfectly positive or perfectly negative, okay? So one thing to keep in mind that we've talked about is that R looks at linear relationships. So if R equals 0, that doesn't necessarily mean there's no relationship. It just means the relationship isn't linear. It could be quadratic, it could be cubic, it could be something else, but it's just not linear. Okay? And don't forget that when we're talking about correlation from Unit 2, correlation is not causation, okay? So we're just looking at the relationship between two variables here. One does not cause the other. We're just saying how they're related, okay? So just keep that in mind as you're doing these examples, okay? So below, you are gonna follow through with this U-try problem, and when you're ready, unpause the video to look at your answers. All right, so in this example, you were looking at, does chocolate make you smarter? Okay, and we've got chocolate consumption versus the number of Nobel Prizes per 10 million residents for for a particular country. R equals 0.791, and you're asked to interpret. When you're asked to interpret the correlation coefficient, there's three things you need to say: its direction, its strength, and its form. Okay, so positive, moderate, linear relationship between X and Y, chocolate consumption and Nobel Prizes. This is a non-negotiable structure. Don't deviate. That is how you interpret a correlation coefficient. So you need those three elements right there, okay? You need the direction, the form, direction, strength, and form. If people in the United States started eating more chocolate, can we expect more Nobel Prizes? No, correlation doesn't mean one variable causes change in the other. There could be something else influencing this particular relationship, maybe like the economy of the countries. What effect does Switzerland have on the correlation? And explain. Switzerland is out here, and if you notice, it's inside this linear pattern we're seeing, this linear positive pattern. So it's going to actually strengthen the idea of this linear pattern by pulling data values towards the line as we go out, okay? So it's inside the pattern and it's an outlier, so it's going to strengthen the relationship. All right, last but not least, let's just go over how to calculate R on your calculator. So I just took this data from the first page and we calculated R using Staplet, but let's use our calculator now, okay? So the first thing you're gonna do is you're gonna take your calculator and you're gonna go to Stat, Edit, we did this yesterday, and enter your data in the lists, okay? So we'll put number of rubber bands in list 1 and distance traveled in list 2. All right, and it should look something like this once you enter your data into the list. I've got X in list 1, Y in list 2. After that, we are going to exit and we are going to hit Stat. We're gonna tab over to Calc. And we're gonna head down to option 8, which says linear regression. A plus BX. I know you see option 4 looks similar to option 8. However, that is not for statistics, okay? So we want to use option 8. And then you're going to enter your lists accordingly. It should say, if you have a yellow calculator, it should say, you know, what do you want X to be? List 1. What do you want Y to be? List 2. And then you hit enter. Frequency list, keep that blank. Okay, and then you hit calculate. And one thing about this is at this point you might not see anything, and that's because your calculator turns the diagnostic off. So we have to go turn the diagnostic back on by hitting second catalog. Catalog is on the 0 button. And we need to go down to diagnostic on and hit enter. And then you'll get this screen. So you should get this screen and it should say done. If you reset your calculator, if you do anything to your calculator, notice right here, this is what you got from the steps above. There's no R value. There's no R squared value. Anytime you reset your calculator, it's gonna remove it and you need to turn the diagnostic back on. So this is an important step to remember. Now that I've done that, I can go back and follow these steps through and I will get this same value that I saw here, but R and R squared should be added below, okay? So stat calc, option 8, one variable stats, X list 1, Y list 2, frequency list clear, hit enter, and then you should see your R and R squared value, which we'll talk about those later, but right now we just need R. And here you go. Notice that that R right here we got is 0.992. That's the same R that we saw from Staplet earlier, okay? Super important that you know how to find this on your calculator. Practice over and over. Listen to the steps. Step 1, enter your data into the calculator. Step 2, stat calc, linear regression. And if you run into an error where you don't see your r or r squared, you've got to turn your diagnostic on, okay? This is something that you have to know how to do on your own. All right, have a great day. Bye.